Hello everyone. I would present my research on helium bubble characterization using artificial intelligence. I think I have been working with many students from our group, Julie, Sydney, and have talked with Steve several times. I haven't mentioned other co-authors here, and they play prominent role in the industry, but I would like to know if they want to be included in the presentation. So I didn't mention them. Some of them are from big tech companies. I tried here. So first of all, I would try to apply a big field, artificial intelligence, into our field, which we know is nuclear materials. And what the purpose is to automate a lot of things that we do. Now, what are the things that we can automate? We can definitely automate something related to the characterization of different microstructural defects that we see into our samples using microscopy. So I have tried to apply this entire field into characterizing helium bubbles that we see in the microscope.
They're not, the online folks aren't able to hear for some reason.
Right. Okay.
But I think if you unmute, we're going to get the right.
So if you mute the speakers here, but leave the computer unmuted.
Okay.
Okay, sorry about that. So let us try to understand what is artificial intelligence. Artificial intelligence is basically we are looking for a computer program that can sense, reason, act, and adapt. It's more automated. And under artificial intelligence is something called machine learning. What is machine learning? Machine learning consists of various algorithms whose performance improves as they expose to more data. Now under machine learning comes the deep learning, which I am using. And when we talk about deep learning, we definitely connect directly to the neurons. Now what is deep learning? Deep learning is a subset of machine learning in which multi-layered neural networks learn from vast amount of data. And this is the subset on which I have been working on for past now many months. And I'm ready to present, one of the main results that I've also written a manuscript. So what is it? Let us see how did we apply it to our problem. So here, so you will hear this term again and again, deep learning and CNN. So under deep learning, CNN is the main algorithm that we are using. So CNN stands for convolution neural network. Now, what is the objective? What I am trying to do? I am simply trying to present this kind of an image to the computer, and I want that computer to tell me whether it's a void or a bubble or a background, and it should be able to just label it. Imagine every day we do microscopy and we have at least 50 images that we take when we come out of the lab, and we have an algorithm that we put these images into, and that tells us that this is a void, this is a bubble, or this is a background, and our job is done in like 5 minutes. So the idea is to reduce all that efforts, and I have applied this algorithm. Now, it's a simple thing that we have applied. We have taken these binary images where, black and white images, where, it's pretty easy. But this algorithm is basically adapted from a classical use of CNN. So in this image, you see that there's an example. You give an image to your network, and you want that image should tell you either it's a dog or a cat. So that means your network is able to detect the object, and here the object is dog or cat. And these kind of algorithms, they are widely available these days, where you can detect in an image where it's male or female. And I took these algorithms and adapted to my image. So finally, CNN is used for object detection, and I am detecting voids or bubbles. Now let us try to see what is CNN. So CNN is convolution neural network. That means it is made up of neurons. And there is an algorithm mathematically that takes into it, which is known as convolution. On paper, or when you have a cartoon, you draw this diagram, CNN, like this. A CNN, it consists of different layers, an input layer, a hidden layer, and an output layer. Here I have provided an example with a kind of an animal or a bird, and I want that my computer should tell me whether it's a bird, it's a dog, or a cat, and I feed it 100 images. And once my network is able to tell me what it is, my job is done. Similar to in our case, I give an image consists of voids, dislocations, bubbles, and it should be able to tell me whether it's a dislocation, it's a void, it's a helium bubble, or it's an edge dislocation, or a precipitate. Why not? And I'm trying to create that system here. So to begin with, this is how a basic representation looks like. You give your network an image like this, here is of a bird, versus here you give it of our microscopy. And this image is fed into an input layer, and now it goes into another layer. There the entire mathematical operation takes place, which I would explain in the following slides. And then we have an output layer where it tells me the probability whether it's a dog, it's a bird, or a cat. And in our case, whether it's a dislocation, voids, helium bubble, or a precipitate, right? So this is the final model looks like. So we give an image. I'm trying to give an example of an animal here, and I want my system to detect that it's an animal, or system to detect that it's a void. It goes under this series of mathematical convolutions. I would explain in the next slide what's convolution. And then entire purpose of this thing, many layers that I have shown you, is to convert this image into a series of number. Once the image is converted into a series of number, then it is processed inside these nodes, which consist of a mathematical formula that I would present. And then finally the answer is out. So before I begin, so we have to keep in mind these terms. In the beginning, it's a feature extraction that I would talk about, in which an image is converted into numbers. Then I will talk about how it is classified. This is done by fully connected layer. And then finally is the output, that is in terms of probability. I would now try to explain how are we converting an image to a number. To give it a very simple example, you see on the left side of the screen, I have taken a very binary or a very black and white image. And this black and white image, which will be your voids, you can imagine a void here, that would convert this image into, so you see here, wherever 2 is written, there is a pixel which has given a number to it. Rest, wherever there is a 0, wherever there is a black space, there is a 0 here. So overall, your void or your 2 here can be represented into a number like this. Now, what we want is, finally we want to enter this thing into this kind of a network. So what is happening? This is a grid that we had, which consists of the information from the image. There's a mathematical operator which simply converts this 2 into 2 matrix, a 2-dimensional matrix, into a unidimensional matrix. Because here you see that they are simple inputs x1, x2, x3, x4. Now what happens? So x1 is directly connected to 0, x2 is directly connected to 0, x3, and so on. You will have x4, x5, x20, x21, and you will have something is connected to 87, 240, 210, and finally we are able to give the input the signature of the image, right? And what happens here? So then all these inputs, so x1, x2, x3, they are fed into here. So what it is nothing. It is simply an Excel sheet with different input files of x1, x2, x3. And this one, it takes all input from all x1 and x2, x3, take different weights. For example, for the first one, weight would be 0 because it's a 0. Second one, weight would be 0 because we don't have any information about there, it's black. Then when it comes down, we have some numbers here, it takes some weights. So it multiplies these inputs with certain weights here, and it's a very simple linear, that we know the equation of a line here. Y is equals to mx plus b, and it is what it is doing. So simple CNN, when you open it up, it is a very, very simple mathematical formula. But what makes it a little bit complicated is we have got many inputs. So computation time is very strong. We cannot, just create this thing on an Excel sheet. We need special systems. So all these nodes, it simply computes, basically H1 is taking all the inputs and just adding them. So W is a weight. Same thing H2 is doing. H2 is also taking inputs from x1, x2, x3 and adding them and giving you another Y. Then x3 is also doing the same thing, and continuously there is a nth formulation is done in your computer. And then out of this thing, we apply a very simple formula and convert all these outputs that we have into your something from 0 and 1 and able to create this binary kind of an image. So till now we are doing a process of converting an image to a number and how that number is put into this formula, and then it gives us a probability distribution. And these links and the arrows that are there, that we famously call them neurons, and everywhere you hear about, this is a field which is coming up very strongly, very, very strongly. And every organization with a TMS, they have special session of applying artificial intelligence to real material science, and characterization is one of the main part. So I'm sure in your career you would be introduced sooner or later with this. Now this is how finally it works, and now let us try to see, going into very detail, how it is happening. So we are detecting features as a first step. In our case, we are detecting loops or voids or dislocations as a first step. This is an image that is fed into a computer, and when the image is fed into a computer, it divides the image into different features. For example, here on the screen you see 9, and 9 has different features to it. It has a feature that is a top circle, a straight line, and a diagonal line. Similar to the features that we have, a dog would have, always his ears down, and the cat will have always its ears up. So that is how it tells you it is dog or cat. First of all, it tries to learn each and every feature of the object. So in your case, it would try to learn feature of the bubble, which would be a circular shape, a void, which would be a polygonal shape, or a dislocation loop or a line. Now, how does it, reading it, what is convolution here? So this is an image here, and you see here it's now in the form of -1 and 1. Same thing, 1 or 0 that I presented. It's a 9 here, right? This is an image that you give, and computer makes it into this 1 and 0 form. And now what do? You apply a filter on top of it. What is a filter? It's simply a mathematical matrix. Here you see a 2-dimensional mathematical matrix that is 3 by 3 dimension. And convolution would simply the multiplication of this matrix over here. So you take it and you scan this matrix over this image, and you keep on scanning it, and this is famously known as taking steps, and you keep on scanning it, and here you get a mathematical number of these two as 0.11. So what does it do? Now go here. So this was the image here. It was an image like this. We apply something, a filter or a feature extraction on the entire image. So here when it goes, it gives you a number. When you take it down on the slant height, it would give you a number. You take it at the bottom, it will give you a number. Why I am making this big image into a smaller image to improve computation? It's not possible that I can give such a big condensed image to my network. Now this is an example here. Ultimately you give this any image, it could be void or dislocation. If it is a circular, it will give you a number as a multiplication, right? 1 here, so it knows there's a loopy behavior, so it will give you a number here. For a 6, it knows we multiply a filter to it, it knows loop and it gives you a feature here. For 8, we know there are 2, circular thing, it could be helium bubbles, and it gives you a number at the top and here. Similarly for 96, it will give you a number here and here. Finally, you give variety of images which consist of either your voids, bubbles and dislocations. Wherever there is a void and everything, it will immediately know, right? It's a number. And if it's not there, it won't give you anything, right? It's a dislocation. On those cases, it won't classify it. So this is a very simple example. It's a very, very complicated image. It's an image of an animal with different features. And finally, this image is converted into a number, a matrix of numbers. This is how you convert an image, by simply multiplying it with a filter. And you are getting all these numbers filled here. And we know wherever there is an I or a loopy character, it is able to give you a number. In this case, you will have an image and you will have a void. If you replace these by voids, and you will have a number 1, 1, 1, and 1. So this is how feature mapping is done. This is how ultimately your void image or dislocation image, or here a simple example that I've given for explanation purposes, converts into your matrix consists of numbers. So again, the same representation is given. Now here, when you get this number, when your image is converted into numbers, you convert this 2 by 2 matrix into unidimensional, and they become x1, x2, x3 till xn, and they are fed into these mathematical operations where you do the same y is equals to mx plus c operation, where you have different weights. And so this is a very simple thing. If this is your void, this is your filter, you get this matrix, and now we apply other mathematical formula because we want everything to come between 0 and 1. And then your image is further processed, further simplified, and it becomes to 0 and 1. And it becomes easy for the computer to understand. So finally, there is a step, pooling step after filter that comes, and your image, which was this, is converted into these small numbers. This big image or complicated image is converted into these small numbers, where each number consists of a particular feature of your image. And this is what we are giving into your final input layer. So I think I've gone through all these things here. This is very simple, again, steps that we did. We did convolution, we did pooling, and finally, and you can keep on adding these steps again and again, and make a very complicated network. You can add multiple layers like this, and can make it much more complicated. And finally, you are able to detect whether it's an animal here. In our case, it would be bubbles or voids. Now, this is what we did. This was our image, which consists of your voids here, as you see. I will go through this in our TM class as well, that whenever it's a polygon shape, we never call it a bubble. It has to have a pressure which is equal to the surface tension. And this is all here are voids, and this has been marked by a lot of images are marked by Sydney, a lot of images are marked by Julie, because we train our network. We have to give them initial training network. We have to give them initial images. And then it gives us the final answer. So here you see, I made a similar representation. So here there is a void, which is, I made it -1, because here is the information present, here is the information present, here is the information present, and so on. I've just presented for easy representation. Now, same thing goes, we have a filter that we just call from the computer, and it tries to extract the feature, right? And it tries to make this big matrix here into a very simplified form, into a simple matrix that I showed you of very minimum numbers for easy computation. So this is how it is. It will, there's a filter that I would call. This filter is nothing, it's simply some numbers, and it would give me these positions and location. On paper, how does it look like, a CNN network? I run these programs in Python, and when I run them in Python, I want that one of the TEM exercise, at least one class we do it. So what happens is, it's very simple when you write it. It's a 5-line program. And into this, you open your Python sheet, you start creating a model, and you create a model like this that you want to create a convolution model. You call a filter, there's a shape of a filter, and there is a mathematical that you want to use as a ReLU. ReLU is a function, it's a mathematical function. And then you add a pooling layer. So basically you are creating this model step by step. You want to create a sequential model, is a sequential here. You want to do convolution, that is you want to apply filter to this image. And then you have a shape, this is 115 to 150, it's a pixel shape here. And finally is a mathematical model. And then you flatten it, that means you convert this 2D matrix into 1D. And finally you created this part of the model. And now you are creating the second part of the model. So on paper it's a very simple activity which I am telling you, to step by step. And finally your answer is here. So this was done, similar work has been done by one of the person from which I took this idea. So the beauty of this entire system is that you can create your own network. You can decide how many layers you want, how many convolutions you want to do, how many regress you want to be with your system. More regress you are, more computation time it would take. So this is the entire network that I took online from a very good paper, and they created a network like this where it simply, all these layers, they are simply convolution layers and pooling layers and all the layers that I explained, and you can literally create in a Python computer. So actual procedure, what we do, we have a lot of images, and once we have the images, we divide them into train. So first of all, we train our model. This is a supervised model in which we have to give images which were labeled by some of the students here. Then we divide these images into validation, that I give another folder to my computer and tell them, hey, validate it. That tell me that it is working properly. Then I can bring finally any images from outside the world and can test in my system, and my system works. Because it takes time to label, we have an artificial system of image augmentation. We can augment the images and create 10 images out of one. We can slightly change the angle, we can slightly rotate them, and different images are given to the computer. And finally, this is fed into a CNN network. There's a different Python files, and you can finally get a system to work. Now, this is what we got. So we give our computer these images. These were the images that my computer gave. These were the images that were labeled by the students. And here is the superimposition of both. So you see here, most of them, this was the ground truth, which you call an actual image. The white one that you see is the predicted map. And when you superimpose, most of them superimpose on each other. But still not perfect, right? There is still a little bit of, you see an astigmatism that you call, a little bit of drift that you call. And what is that? So if I draw it, so this is like a cavity which was already present, that was a truth which was present in my image, versus it has predicted. There is a kind of little bit shift. So ultimately, when we have these images, I want to make sure that they are exactly same as of the image I provided. For that, what we do is we try to optimize our model. And what we use is loss function. And there are multiple loss functions that are available in the literature, and you can choose according to what you want. Now here, what is happening here? This is the number one task in machine learning models, that we have to optimize the loss functions. We want minimum loss. Minimum loss would mean we want the final answer to perfectly superimpose on the ground truth. So for that, we do simple analysis like intersection over union. In the intersection over union, we simply, have these two predicted and ground truth who are intersecting here. You see that there is a zone where, they're intersecting in some cases. And we want that they should fall on each other. So we simply calculate IUU, that is number of pixels that are covered by here, number of pixels that are covered here, and we want to make it the answer on top, that both of the pixels are equal and overlap. And we can optimize it, and we can send this thing back into our neurons, because this simply comes by playing various parameters. We keep on playing it, and it keeps on improving it. Now here, this is the main thing that we play with. You see here, this is what is the predicted by your CNN, and this is the truth, which was masked by Sydney here, I think this one image. And then I overlapped it, it became like this. Now in this, we try to have a matrix. So there is a true positive, true negative, false positive, and false negative. So when the computer takes it, the images where it is actually overlapping with the results are good, we call it true positive, because it's, it gave us a positive answer here. Where system is giving us black, it is actually black, and we call it as a true negative. But there are places where you see here, in this one there was nothing here, but your image, it gives it a positive, so it's a false positive. And here, you will see here that system forgot to give us the exact white and give us black, so it is false negative. And by playing with this, we can calculate the accuracy of our model. We say that true positive, true negative, all the true that it is here versus whatever it has shown to us, we add, and it gives us accuracy. Similarly, we can calculate the precision by dividing the true positive versus your true positive versus false positive. And similarly, we can call other accuracy measurements. These are all the parameters that tells you. So basically, I am doing a very simple game in which I am trying to compare, find the difference game that you do on your mobile. I'm trying to compare the differences and trying to optimize it in all the way I could think, in terms of boundary, in terms of precision, in terms of accuracy. Now, here is an example that they have given about precision and accuracy. What is the difference? So, if something, in the image like this, it is still accurate because it is able to tell you that where are my voids. But maybe it's not precise because it's not overlapping. So, this is something from here. We see here that if we know this game, right? And if our darts, they are still in this round, it's accurate, it's still in the round. But till the time it's not here, it's not precise. So for us in machine learning, precision is the highest thing that we look for. And if we don't have precision, we'll have the image that is shifted, we will have wrong, false positive, false negative, we have seen it. And this is something we want, a very precise model.